Okay, good day. This is AP Calculus. I am Mr. McColley. This is section 6.2. I want to keep it rolling, so let's jump right into it today. Today we're going to talk about using the separation of variables to solve simple differential equations, and then we're going to use exponential functions to model growth and decay in applied problems. And again, this is something that you guys have seen over and over again, so I'm going to keep the examples to that one pretty short. I'm going to only have one, and then like I said, you've seen it. It's going to come back to you. It's not a big deal. All right, so let's talk about solving differential equations. One of the most basic methods to solve differential equation is through the separation of variables. Now, I introduced this in the last sections just so that we can start having the same vocabulary. But let's talk about this one here. It says find the particular solution of the differential equation given that the function y passes through this point. So we are looking for the particular solution to this equation. So we want to get y by itself. Now what we want to do is we're going to put the y's here on the left, and we're going to put the x's on the right. Now so remember, this expression for derivative can be thought of as a fraction. We can separate it as a fraction. So to move the y's on the left, I have to divide both sides. So I'm going to get 1 over y when I divide times the differential of y is equal to 3/4 dx. So now I have all of my x's and all of them on the right hand side and all of my y's on the left hand side. So all we're going to do here is we're going to integrate both sides. Now the integral of 1 over y is just the ln of y. And then the integral of 3/4 x, or 3/4 dx, is 3/4 x plus some constant c. And again, yes, when we integrate on this side, there should be a constant, but we just move it over to the other and combine constants. Excuse me, you really need to get used to that because we're going to be combining constants quite a bit here as we move forward. Now, we want to get y by itself so we can have a function for y. And remember that log base b of x equals y if and only if b to the y equals x. So since ln is e, or is log base e, we can say y equals e to the 3 over 4x plus c. And remember that if you have a to the x times, or excuse me, I was going backwards here. If you have a to the x plus y, that's going to be equal to a to the x times a to the y. We've talked about that way back in Algebra 2. So here's what I'm going to do. I'm going to separate this c out of the addition in the top with multiplication and say that y is equal to e to the c times e to the 3 over 4 x. Now, e to the c is a constant, and so we're just going to combine these two into a new constant and call that c again. C times e to the 3 over 4x. Now this thing right here, this is our general solution, G-E-N-E-R-A-L. But they give us an initial condition. When you plug in 0 in for x, you get 10 out of this particular problem. So that's what I'm going to do. I'm going to figure that out. So I'm going to go 10 is equal to c times e to the 3 over 4 times 0. Now that becomes 0, and so e to the 0, anything to the 0 power other than 0 is 1. And so we end up with c equaling 10, and now we can rewrite in the final form and say y equals 10 e to the 3 over 4x. This is our particular solution. Because there are no variables other than the independent variable and the dependent variables. There is our solution. Now what that brings us to is the exponential constant for exponential growth and decay model. So if y is a differentiable function of t such that y is greater than 0, then the derivative of y is equal to kt for some constant k. C is the initial value of y, and k is the proportionality constant. Exponential growth occurs when k is positive, and exponential decay occurs when k is negative. So how can these two things, ky and ce to the kt, be equal? How can they both be equal to those two values? Well, let's talk about that. If I look at this thing, I can rewrite y prime as dy over dx. That's how I write it. That thing is equal to ky, and so just like in the last one, we're going to separate our variables. We're going to keep our y's on the left-hand side, our x's on the left. I said that backwards. My y's on the left-hand side, and my x's on the right-hand side. Did I do that right? Yes, I did. I felt real stupid if I hadn't. So dividing both sides by y, multiplying both sides by dx, I get 1 over y dy is equal to k dx. Now we want to integrate both sides. Since k is a constant, I'm going to move it out. And so what we have here is we're going to have the integral of 1 over y is again just the ln of y, and that's going to equal to k times the integral of dx. So the integral of 1 dx is just x plus some constant c. And so let's do one more step and say that distribute here, and k times x plus, when I go k a constant times c a constant, I get a new constant c. So this c and that c aren't the same. Get over it. And so again, using the definition of logarithm, I got y equals e to the k x plus some constant c. And again, we're going to separate that into, because of the addition here, and we'll have y equals, let's see here, I want to say e to the c times e to the k x. And again, e to some constant is just some new constant, so I'm going to leave that ce to the kx. Well, this is my value for y, but what we were trying to show is that y prime is equal to k times y. Well, I got to know what y is before I can do that, but if I start with that, y is equal to c e to the kx, and that's an x there. We'll try and make it a little bit better. If I do the derivative of this thing with respect to x, I get dy over dx is equal to, and a constant you leave alone, e to the u. The derivative of e to the u is just e to the u times du. So we got ce to the kx, and the derivative of just kx is just k. So I end up, if I reorganize, I get k times ce to the kx. Well, we just saw right here that this thing is y. We know that this particular dy over dx is just y prime, and so this thing is ky. So we've just shown that if you have the derivative of y equaling to ky, you can replace that, just skipped over it, with ce to the kt. And that's, we're going to do an example of that later on. All right. So starting off with some simple examples. So they want us to solve the differential equation, and these are all, for at least these first couple, are going to be general solutions unless they give us some information. So here they go, dy over dx is equal to, is not equal to 6 minus x. Well, if I want to separate my variables, I can say dy on the left-hand side and 6 minus x dx on the right-hand side. And now that I've separated the variables, I can take the integral of both sides. The integral of 1 dy is just y. And then the integral of this expression, we could do it a couple different ways, but let's just keep it simple and do a simple power rule on each term. So I'll have 6x plus, actually it's going to still be minus, I've got x to the first, so it's 1 over 2x to the 1 plus 1, which give me 2, plus some constant c. And since I'm already at 10 minutes, what I'm going to do is I'm going to say that is good enough, remembering that you should probably put this in descending order. All right, let's move on to number 12. Number 12 says the rate of change of p with respect to t is proportional to 25 minus t. So again, when they say the rate of change of p, right off the bat, rate of change, derivative, dp over dt. Remember they say it's proportional, so we need a proportionality constant, and it's proportional to 25 minus t. So now we have something that's very similar to the one we just did. We want to separate our variables here, so we're going to put all our p variables on the left-hand side, all of our t variables on the right-hand side. So dp is going to equal k times the integral of times 25 minus t dt. And we're going to take the integral of both sides. Since this is a constant, I can leave it out. The integral of 1 dp is just d. I said what I wanted, but I didn't write it. The integral of just 1 dp is p. We have k times the integral of what's inside here. And so we could do, again, we could do it a couple of different ways. The easiest way is just do the simple power rule on each one, and we'll have 25t minus 1/2 t squared plus some constant c. Distribute the k if we wanted to, so p equals 25kt minus 1/2 kt squared plus k times c, a constant times a constant is a constant. So this c and this c aren't the same, but there you go. And again, we could probably fiddle with that, but there you go. All right. Example 22. Now, this one we're going to relate to this expression here. So I'm just going to bring this one down a little bit closer so I can see it and show you what it is. So they say the rate of change of n is proportional to n. So when they say that, what they're essentially saying is that n prime is equal to kn. So we have a situation where we have n prime is equal to kn. And so what we can do is we can go right in and use this formula that we came up with and proved earlier, say that n prime is equal to some constant c e to the kt if we wanted to. Now, that's the easiest way and the simplest way to do it, but I would like to make sure that you do see how to do it through integration. So I'm going to rewrite this as dn over dt is equal to kn. And again, we're going to try and separate the variables. So all my n's I'm going to keep on the left-hand side. My t's I'm going to move to the right side. So I've got 1 over n dn is equal to k dt. We're going to integrate both sides. K is a constant, so I'm going to leave that on the left-hand side of the integral symbol. And then the integral of 1 over n is just ln of, and this should be a capital N. I changed my, you don't want to change your variables there, McColley. Got ln of capital N equals kt plus some constant c. And then I'll have n equals e to the kt plus some constant c. Separate those values. We've got n equals some new constant c e to the kt, just like we did in a previous problem. But we don't want this expression. We want n prime. We want this. So n prime, the first derivative of this expression with respect to t, is going to be the original problem, c e to the kt, times the derivative of the exponent here, so just k. And so n prime is going to equal to k. Now this expression here we just showed was capital N, so I've got my n. So either way, you can either memorize the rule that we showed here, or you can do the separation of variables. I know that's a lot, and we probably could skip some steps, but that just gives us a general idea. Now what they also say is they want us to find the particular solution to this thing. So they want to know what, let's see here, n is proportional to, they say when t equals 0, n is equal to 400, and then when n is equal to 1, or t is equal to 1, what happened there? I don't want that. When, there we go. When t is equal to 1, n is equal to, let's get this right here. See, I screwed up. There's 400, and this one should be 250. All right, so here's what I'm going to do. I'm going to start with this. Let's see here. They say write and solve the differential equation. Evaluate the solution of the specified independent variable. What is the value of n when t equals 4? So they want n when t, they want to know n. Put a question mark there, when t equals 4. Well, here's what I'm going to do. I'm going to use this, not that, don't move that. I'm going to use this equation for n, and I'm going to try and solve this thing. So I've got my n equals ce to the kt, because they don't want n prime, they want to know what n is. So I need to solve that. So when t equals 0, so let's just plug in for that first one. We'll just rewrite it and do it right. So n equals 250. 250 equals ce to the k times 0. When time is 0, so e to the 0 is 0. C equals 250. I can use that 250 for the second one and say n equals 400. 250 is my new value for C, e to the k times 1. And now we can solve for just e. So I'm going to divide both sides by 250. So I got 400 over 250 equals e to the k. When we're solving for an exponent, remember from a ways back, you're going to take the ln of both sides. So the natural log of 40 over 25, I hope you don't mind that I cancel my zeros, equals the ln of e to the k. The k comes down and cancels because e to the 1 is just 1. So I end up with k equaling the ln of 40 over 25. So k equals, clear out of this, ln of 40 over 25. That's my k, so 0.47. And since we got all zeros there, we'll just leave it 0.47. So k equals 0.47. And so my final equation is n equals 250 e to the 0.47 t. That's my final equation, but they don't ask for that. They want to know what is n when t equals 4. So n equals 250 e to the 0.47 times 4. So let's do that. 250 times e to the 0.47 times 4, and we get 1638 37 point, or 0.376. So 1638 376. There is the value for n when t equals 4. All right, not bad. Number 36, it says in exercises 33 through 40, complete the table for a radioactive isotope. So this is going to be the big review question, and I'm hoping that everybody remembers all their exponential and logarithm stuff. If not, I'm going to write them down as we go. But number 36 says that the radioactive isotope C14, and they write it like that, has a half-life of, let's see, where is it? 5,715 years. 5,715 years. That's pretty long. They say that they want to know the initial quantity, we don't know that, we got to fill that in. They want to know the amount after 1,000 years. And then they say that the amount after 10,000 years is, what's left here? How much? 3 grams. So we got to figure out the rest of it. Okay. So, exponential growth. A equals PE to the RT. Let's break it down here. What we already know is and if you wanted to have this as R as K, it's fine. It doesn't really matter. What we already know is that in 5,115 years, there will be half of whatever your initial amount is present. So just to keep it easy, I'm going to start with 1 unit, whatever that unit may be. In 5,715 years, there will be 1/2 of that amount left, and we want to know the rate at which it's decaying. So 5715. If you look at this, now I only have one variable, the variable r. All right. So what we'll do is we'll solve for r, and so I've got a 1/2 equals e to the 5715 times r. We're going to take the ln of both sides. And so the ln of 1/2 is equal to, ln and e cancel out, so I have 5715 times r, and r equals the ln of 1/2 over 5715. So if I go to my graphing calculator and I say the ln of 0.5 divided by 5715, I get something pretty darn small. So that's my rate of decay per year. So just to be safe, I am going to store that in A. So anytime I pick up A, anytime I type in alpha A, it's going to give me that number, and I can use that to multiply. All right, so that's my rate. I know what that rate is. We'll call it, I don't want to use A because I have that, but we'll call this just ANS for right now. All right, so that is my rate, which I know. So I have an amount after 10,000 years. So here's what I want to do. I want to find my initial quantity. What did I start with? Well, if I finished with 3 and I want to know what I started with, well, that's P. That's just P. That's my starting amount. So I've got EANS times 10,000 years. Another 0. Okay. This expression here, I can calculate. This is just a number because I know everything. Just divide both sides by that. So P is going to equal 3 over e to the ANS times 1,000. Fairly straightforward. So I go to my graphing calculator. I go 3 divided by the quantity, second, E, and I don't need second. I need alpha A, that's this number, times 10,000. And then we want to close that parenthesis, hit enter. So my initial amount is going to be 10.089 grams. I think we're starting with grams. Let's make sure. Yep. So P equals 10.089 grams. 10.089 grams. And my G's and my S's are starting to look the same. All right, so I want my amount after 10,000 years. Well, if I again start with A equals PE to the RT, I know what my initial amount is. We just figured that out. 10.089. E, we know what the rate is. It's that ANS that we found over here. And the time is just 1,000 years. This is the easiest one to calculate because all I got to do is put it in the calculator. My A equals. So I start with second answer. That's this number. Second E. We're going to use the rate that we found at the beginning. So not second, we just want alpha A times, now not 10,000 years, but 1,000 years. So I hit enter, and so after 1,000 years, we've got 8.937 grams. 8.937 grams. All right, and that brings me to the end. That's a lot of stuff, I know, but we got through a bunch. Have a good one. Bye.